We look at these ancient stone tools, perfectly shaped, and you naturally think the secret is all in the rock itself, right? How it flakes and breaks.
Yeah.
But what if the person making the tool, what if they had a lot more say in that shape than we usually give them credit for? Okay, let's unpack this. Welcome to the deep dive.
Today, we're heading way back, Middle Paleolithic. We're talking, what, maybe 200,000 to 400,000 years ago? And we're exploring the Levallois technique.
Yeah, and this wasn't just, randomly bashing rocks together. It was a really sophisticated method. Tells us a lot about how early humans were thinking, potentially.
Definitely. And for this deep dive, you shared a fascinating, really recent piece of research. It's called Controlling Levallois, the effect of hammer angle of blow on Levallois flake morphology and fracture trajectory. That's by Lin and their team, just out this year.
That's the one. Really interesting stuff. So our mission today is to really get to grips with this study. We want to understand something pretty fundamental. How did the angle in which these ancient toolmakers struck a stone core, how did that actually influence the shape and size of the flakes they were producing?
Exactly. Because it turns out this angle, the striking angle, might be a much bigger piece of the puzzle than we've traditionally thought. Maybe, even more important in some ways than just how the core itself was prepared.
Which is kind of counterintuitive, isn't it?
It is, because for a long time, when archaeologists looked at Levallois technology, the spotlight was almost entirely on the core. How was the stone core shaped beforehand? That was seen as the key.
A pre-planning stage.
Right. The idea was that by carefully crafting the surface of this core, these ancient knappers could essentially, predetermine the flakes they were going to knock off.
Design them in advance, almost.
Sort of. The Levallois core, as the paper points out, has this really specific design. It's got two main surfaces, worked from both sides, bifacially worked, and they meet at something called a plane of intersection.
Okay, a plane of intersection, like the middle meeting point.
Yeah, think of it like that. How fractures interact with this plane is really central to understanding Levallois. And then you've got the surface they actually prepare to strike off flakes from, the debitage surface. And this was carefully shaped with specific curves, convexities, and ridges.
And the thinking was these prepared shapes were basically guiding the fracture.
That's been the main idea, yes, that these features were the primary drivers of the final flake shape.
So the core was like the template, and hitting it just released the preset form.
Pretty much.
But this research suggests we need to zoom in on the actual hit, the action of striking the core.
Exactly. Specifically, the angle of that impact, what the researchers call the angle of blow, or AOB for short.
AOB, angle of blow.
And this AOB, it's defined as the angle between a straight line coming down from the hammer, perpendicular to the hammer's striking axis, and the surface they're actually hitting on the core, the platform surface.
Got it. Hammer path versus platform surface.
And here's where it gets really interesting. For years, the main explanation for how flakes actually break off. There is a model from Cotterill and colleagues back in the 80s. That model suggested flake shape was mostly about, how stiff the flake itself was as it was forming, and the shape of the core surface it was breaking away from.
Okay, so core shape and flake physics, basically.
Right, and crucially, this idea didn't give much importance at all to the angle of the hammer strike.
So the AOB wasn't considered a major factor.
Not really. Cotterill and his team even argued that the person hitting the stone, the knapper, couldn't really control the angle of the force transfer that precisely. They thought the breaking flake itself sort of self-corrected the fracture path.
So the stone breaks how it wants to break, guided by its shape.
That was the dominant thinking for a long time, yes. The fracture path was mainly determined by the core's surface geometry and the stiffness, with the hammer angle being, a relatively minor detail.
But as this new research points out, and maybe as you hinted earlier, that doesn't quite match up with what people who actually try to make these tools have seen.
Precisely. Modern flint knappers, people who replicate these techniques today, they've long suspected that the angle you hit the stone at really matters.
Practical experience versus theory.
Exactly. Researchers like Schlanger and Van Peer, they've observed modern knappers often using a more angled strike, a higher AOB, when they're detaching Levallois flakes specifically. And there's a growing body of experimental work showing, yes, the hammer striking angle does indeed change the size and shape of the flakes you get.
So experiments were already pointing in this direction.
Some were, yes. Earlier experiments even showed that hitting the core more directly, more perpendicularly, so a lower AOB, that tended to create larger and heavier flakes. So you had this kind of disconnect, right, between the established fracture mechanics theory and what people were actually observing and experiencing.
And that's where this new study, Lin et al., comes in. They wanted to really nail this down with a controlled experiment.
Yes, exactly, to properly isolate this AOB factor.
So how did they set it up? It sounds tricky.
Well, it was quite clever. First, they used standardized Levallois cores, but not made of flint. They used soda-lime glass.
Glass. Why glass?
Because glass is very homogeneous. It breaks in a really predictable way, much more so than most natural stones, which can have hidden flaws or variations. It fractures conchoidally, like flint or chert, but consistently.
Okay, so it takes out the variability of the raw material.
Precisely. And these weren't just random glass lumps. They were created using a super precise machine, 3D milling, to perfectly replicate the shape of a real flint-napped Levallois core. So every single glass core they started with was identical.
Wow, that's amazing control.
It is. And they even made the 3D model available online on Sketchfab, so you can actually go and look at the core shape they used.
Cool. So identical glass cores. Then how do they hit them?
They used a custom-built mechanical flaking machine, a robot knapper, essentially.
A robot knapper.
Yeah, based on a pioneering design from earlier research. This was absolutely crucial because it allowed them to control the hammer strike with incredible accuracy. No human inconsistency.
Right, takes the human wobble out of it.
Exactly. And with this machine, they systematically changed two key things. First, the angle of blow, the AOB. They aimed for 3 different angles. 0 degrees, which is straight on, perpendicular, then 10 degrees, and 20 degrees representing more oblique strikes.
Okay, 0, 10, 20 degrees.
Although they note the actual AOB varied slightly because of the setup, the control was still very high. And the second thing they varied was the platform depth, or PD.
Platform depth. What's that?
That's basically how far back from the edge of the core platform the hammer blow is aimed. Imagine hitting right near the edge versus a bit further in. Ah, okay. So hitting closer or further from the edge.
Right, so they had these 2 variables.
Yeah.
AOB and PD.
And after the robot did its striking.
They meticulously measured everything about the flakes that came off. They used a 3D scanner to capture the exact 2D outlines. They measured linear dimensions, length, width, thickness, weighed them, of course, and they even measured the force required for the machine to actually detach each flake.
Force measurements, too. Okay, comprehensive.
Very. And they didn't stop there. They also analyzed the path the fracture took through the glass. They did this by looking at cross-sections and calculating the angle of that fracture plane relative to the platform.
Wow, okay, so they really tracked the whole process. What were the big findings then? Let's start with, say, flake weight and the force needed.
Okay, so one clear result confirmed what you might expect. Hitting further back on the platform, increasing the platform depth, PD, generally resulted in heavier flakes. Makes sense, you're taking off more material.
Right, deeper hit, bigger flake. But the really key finding for our discussion relates to the angle of blow. They found that striking at a higher AOB, so a more angled oblique strike, consistently led to lighter flakes.
More angled means lighter flakes.
Yes. And conversely, for any given platform depth, striking the core more directly, more perpendicularly so, a lower AOB, like 0 degrees, consistently produced larger and heavier flakes.
Ah, so the angle directly impacts the mass of the flake produced.
Absolutely. This strongly backs up those earlier experimental hints and really underscores that the napper's action, specifically the angle, directly influenced the size of the flake, not just the pre-shaped core dictating everything.
Interesting. What about the force? Did the angle affect how hard they had to hit?
Well, they did find a positive correlation between flake weight and the force needed to detach it. Heavier flakes needed more force.
Which also makes sense.
Right, and that fits with previous research too, but interestingly, the angle of blow didn't seem to significantly influence that particular relationship. So whether you hit straight on or at an angle, a heavy flake still needed proportionally more force than a light flake.
Okay, so the angle changes the resulting weight, but the force-to-weight ratio stays roughly similar regardless of the angle.
That seems to be the main point regarding force and weight, yes.
Fascinating. Okay, so angle affects weight. What about the actual shape? Did the AOB change how the flakes look, their geometry?
Oh, absolutely. This is where it gets really detailed. Even though the cores were identical to start with, both the platform depth and the angle of blow significantly influenced the final size and shape.
Both factors mattered for shape.
Yes. As expected, increasing the platform depth generally led to bigger flakes overall, longer, wider, but the angle of blow had a more specific, more nuanced effect on the form.
How so?
They found that as the AOB increased, remember that's a more angled oblique strike, the flakes tended to end up narrower. And specifically, narrower and more pointy at the distal end, the end furthest from where it was struck.
So angled strike equals pointier flakes.
Tended to be, yes. On the other hand, a lower AOB, that more direct perpendicular hit, resulted in flakes that were systematically longer and wider for any given platform depth.
Wider and longer with a straight-on hit.
Exactly. And flake thickness also showed an interesting interaction between PD and AOB. At the lower AOBs, 0 and 10 degrees, the thickness increased more rapidly as the platform depth increased. And flakes detached right at that 0-degree AOB, the straight-on hit, had a significantly higher thickness relative to their platform depth compared to the angled hits.
So hitting straight on not only made them wider and longer, but also relatively thicker for the spot they were hit.
That's what the data suggests. So yeah, the angle was drastically altering the final form, the proportions.
It really wasn't just the overall size then. The actual proportions, the geometry of the flake, were being actively shaped by the angle of that strike.
Precisely.
It makes the toolmaker seem much more involved in the final product than just preparing the core correctly.
Exactly right. And this control over shape is explained even further by what they discovered about the fracture trajectory, the path the crack took through the glass.
Yes, you mentioned they looked at that. What did they find there?
When they hit the core more directly, with a lower AOB, like 0 degrees, the fracture tended to travel more inward into the core.
Inward, towards the center.
Yes. And this inward path meant it aligned more closely with that plane of intersection we talked about earlier, the conceptual middle of the core. Following that plane allowed the fracture to go deeper and travel further before it eventually curved up and reached the outer debitage surface of the core.
Resulting in those longer, wider, thicker flakes.
Exactly. In contrast, when they hit at a higher, more angled AOB, like 20 degrees, the fracture tended to tilt outward, away from the core's center.
Outward. So it surfaced sooner.
Correct. It intersected the core's prepared outer surface much sooner. This resulted in those shorter and thinner flakes, and flakes that were often more convergent or pointed at the distal end. The researchers think this pointy shape at higher AOBs might also be linked to a central ridge they had on the debitage surface of their experimental core.
So the angle interacts with the core's surface features too.
It seems so. They even measured the angle of this fracture path relative to the striking platform surface, and they found that this fracture trajectory angle decreased as the angle of blow increased.
Okay, let me get that straight. Higher AOB, more angled strike, leads to a lower fracture angle, more outward path.
Yes, that's the relationship they found. They also saw that longer flakes showed a clear difference in this fracture angle depending on which AOB was used.
This really changes things, doesn't it?
Yeah.
It fundamentally challenges that long-held idea that the core shape was basically the sole determinant of the flake shape.
It absolutely does.
It sounds like the knapper's technique, specifically choosing that angle of strike, was a really important active factor in controlling the outcome.
That's precisely the main implication of the study. It strongly suggests that Levallois toolmakers could indeed influence, maybe even control, the morphology of the flakes they produced by deliberately manipulating the hammer-striking angle.
So they weren't just passengers, they were driving.
In a way, yes. And interestingly, using a lower AOB, that more direct strike, seems to have allowed the pre-shaped convexities on the core surface to have a greater influence on guiding the final flake shape.
So the angle affects how much the core preparation matters.
It seems that way. A lower AOB lets the core's shape speak more, if you like. And this connects really nicely with observations that archaeologists have made about actual Levallois flakes. Often the really well-made ones, the preferential flakes, have a more evenly distributed thickness and quite obtuse wide edge angles.
Okay.
And the researchers suggest that these features could potentially be achieved specifically by using those more direct lower AOB strikes.
That makes a lot of sense. But it's interesting because you mentioned earlier, the paper also notes that modern knappers often seem to use a higher AOB, a more angled strike.
That's right.
If a lower angle gives you potentially better shape control, or at least allows the core prep to work better, why might modern knappers choose a more angled strike?
That's a great question, and the researchers discuss this apparent contradiction. They offer a couple of plausible reasons based on the practicalities of knapping. First, using a lower, more direct AOB might actually increase the risk of messing up the strike, specifically overshooting the core.
Overshooting, you mean hitting it too hard or too deep?
Kind of. If the fracture goes too far inward because of that low angle and doesn't connect properly with the prepared curves on the outer surface, it can actually break off the opposite edge of the platform. It's
Oh.
called an overshot or outrepasse termination.
Okay. That sounds like a mistake.
Generally, yes. It can remove too much mass, potentially ruining the core for further flake removals. Preventing these is a sign of skill. So, using a slightly higher AOB might be a strategy to reduce the risk of that happening.
A bit of a safety mountain, maybe.
Could be. Second reason, striking at a more angled AOB generally requires less percussive force to detach the flake.
Place effort.
Potentially. Remember, the results and other studies show force is related to flake size. Since lower AOB strikes tend to produce larger, heavier flakes, they naturally require more force. Now, if a knapper doesn't apply enough force when attempting a low AOB strike, the fracture might stall and stop too early. This can result in undesirable breaks like hinge or step terminations, where the flake snaps off abruptly instead of feathering out smoothly.
Or bad outcomes.
Also, generally undesirable, yes. So, using a slightly more angled strike might be a way to make detachment a bit easier, requiring less peak force and lowering the risk of those hinge or step failures.
So it's like a trade-off. Lower AOB might offer more potential control via the core prep, but higher AOB might be safer or more efficient in terms of force and avoiding certain errors.
That seems to be the thinking, yes. A balance between control and risk management.
Does the paper connect this back to actual archaeology at all? Did they look at ancient tools?
They did, tentatively. They compared their experimental results, specifically the relationship between flake thickness and platform depth, PD, at different AOBs, with measurements taken from actual Levallois flakes found at a site called Roc de Marseille in France.
Roc de Marseille. Neanderthal, say, right. Middle Paleolithic.
Exactly. And interestingly, the thickness to PD ratio observed on those ancient flakes seemed to align most closely with the results they got in their experiment using the 10-degree angle of blow.
Not 0 degrees, not 20, but 10.
That's what their initial comparison suggested.
So does that mean the Neanderthals there were maybe deliberately using a slightly oblique 10-degree-ish angle?
It's a very tentative suggestion, as the researchers are careful to point out. It's just one site, and many other factors could be involved. The specific raw material used at Roc de Marseille, the exact core shapes they were using, individual knapper skill.
Sure, lots of variables in the real world.
Exactly. But it's a fascinating hint. It shows how we might potentially use these kinds of experimental results and flake measurements to start inferring past knapping behaviors, like the angles they might have preferred.
It really drives home that making these Levallois tools wasn't just about having a well-prepared core. It involved a whole coordinated action, right?
Absolutely. A coordinated knapping gesture involving adjusting not just where you hit the PD, but how you hit the angle of blow, the amount of force applied, all potentially adjusted based on the core's condition and the desired outcome.
Real skill and maybe conscious decision-making.
It certainly points towards a high degree of procedural understanding and motor control. And this brings up important questions for future research, as the paper notes. There's a real need for more studies that explicitly monitor and measure the hammer angle of blow in realistic, ethnographic, or experimental knapping settings with human knappers.
To see what angles people actually use and why.
Precisely. And excitingly, there are emerging methods that might allow researchers to estimate the AOB directly from features left on archaeological flakes themselves. Things like microscopic analysis of the platform area.
Measuring it on the ancient tools.
Potentially, yes. Methods proposed by Liz and colleagues in recent years. And the fracture trajectory angle, which this study measured in the glass cores, could also serve as another proxy to help reconstruct the AOB used in the past.
So, multiple lines of evidence to get at this angle question.
Hopefully, yes. Combining these approaches could give us a much clearer picture of how early humans controlled the knapping process through their striking technique.
It's amazing how much detail we can potentially pull from these stones by looking beyond just the final shape into the physics of their creation.
It really is. And this study also serves as a great example of the value of controlled mechanical experiments in archaeology. They actually successfully replicated some key findings from a similar machine-based experiment done by Dibble and Resek back in 2009.
Oh, they repeated earlier work.
They replicated the relationship between platform depth and flake size, yes. Which is important because it shows that this mechanical flaking approach is robust and yields replicable results. builds confidence in the method.
Good science.
And they also highlight the promise of using automated 3D milling like they did with the glass. It allows for creating highly standardized cores from various materials, giving incredible control for lithic experiments. They even mention they can mill harder rock materials now, like actual chert, which opens up even more possibilities for future studies.
Very cool. Okay, so to try and wrap this up then, if we had to distill it down,
Right.
what's the key insight, the main takeaway from this deep dive into Lin et al.'s research?
I think the main takeaway is that the angle at which you strike a Levallois core, the angle of blow, is a truly critical and perhaps previously underestimated factor in determining the final size and shape of the flake you produce. It's not just about preparing the core perfectly. The way you hit it matters significantly.
So core prep and strike mechanics work together.
Exactly. This research powerfully demonstrates that by manipulating the AOB, ancient toolmakers likely had a considerable degree of active control over the morphology of their flakes. It adds a whole new layer to our appreciation of the skill, the complexity, and the sophistication involved in this ancient technology.
It makes you wonder, doesn't it? If that angle of strike was so critical and potentially controllable, what might that imply about the level of precision they were capable of, about the planning involved, maybe even how these skills were taught or communicated? Could we perhaps see different traditions of striking angles if we look closely across different archaeological sites or time periods? Could that reveal subtle differences in their techniques, or maybe even their cognitive approaches to toolmaking?
Those are exactly the kinds of provocative questions this research opens up.
It certainly gives you something to mull over. Well, if you, the listener, are interested in digging even deeper into this, we definitely recommend checking out the research paper we've been discussing today. That's Controlling Levallois, the effect of hammer angle of blow on Levallois flake morphology and fracture trajectory. Or just look for other studies on Levallois technology and experimental archaeology.
It's a fascinating field.
Absolutely. Thanks for joining us for this deep dive.